All right, one more parametric example for you, and then we'll move on to projectiles. Okay, there's another technique I need to show you. So what we learned in the last video was how to deal with our situation when we have x or y as a function of time, and we could take x as a function of time, figure out what we need y as a function of time. Now, this one is a little bit different. Okay, we don't have anything as a function of time here. So let's read the question here. Particles traveling along a certain path. Okay, got it. If x equals 8, then Vx is 8, Ax is 4 at t equals 2 seconds. Okay. Okay, hold on to that. We're going to come back to that. Determine the magnitude of the particle's velocity and acceleration at this instant. Okay, well, let's write that down. So we've got someplace, maybe to act as a lighthouse and guide us. So we know we're going to eventually need this. We're going to need A is ax squared plus ay squared. Okay, and we're going to need this. Okay, Vx squared plus Vy squared. Okay, so if we get Ax, Ay, Vx, Vy, we're in good shape. Okay, we got it. Now, as far as the Ax and the Vx goes, we might be okay. Let's look up here because it tells us right here, Vx is this and Ax is that. All right, so 8 and 4 respectively. But then it says, it's got this weird thing here. It says when t equals 2 seconds. So what do we do with that? Well, there's no t's anywhere. Okay, we don't know what is going on. Okay, we don't know what's going on. Okay, here's how we think about that. All right, what we do is we're going to say that x, whoa, not like that. We're going to say it like this, that x is some function of time. Now, we don't know what that function of time is, but we know in our problem what it's telling us is that f of 2 is equal to 8. All right? V is going to be f prime, okay? And V evaluated at 2 is going to be equal to 8 also. A is going to be f double prime, and A evaluated at that point is 4. Okay, so the thing here is that we don't know this function. It's okay. That's okay because we know that the function evaluated at 2 is 8. Its first derivative is 8, and its second derivative is 4. Okay, so we know all that information. So we have more than it feels like we might have, okay? But what do we do about y? Okay, well, here's where we go back to the equation that relates x and y, okay? And so we say that y is, it's a quarter x squared, so y is 0.25 x squared. Now, what we'll do, okay, this is kind of like, remember way back in Calc 1, you ran into something called implicit differentiation. Okay, so this is like implicit differentiation and the chain rule had a baby. Okay, that's what we're about to do. Okay, so we're going to figure out the first derivative of respective time for y. Okay, so Vy is a dy dt, which means we have a d dt onto 0.25 x squared. Okay, now then, if we do that, what we're going to have is, of course, the constant stays out front. Okay, then we need the derivative of the x squared term. Okay, so we're going to do this guy. And that gives us a 2x dx dt. Okay, just like that, because we don't know, we're taking the derivative with respect to time. We don't actually know what x is as a function in time, but we can write down that some generic dx dt, we don't know what that is. Okay. All right. So now let me rewrite this in the way that we're going to do it moving forward. I want you to see it in little tiny baby steps. Okay. And so sort of to put it all together in a bigger sense, we're going to say that Vy is y dot. Okay, and I'm going to go 2 times 0.25 gives me a 0.5 x dot. Okay, so remember x dot, same as dx dt. Okay, just like that. Okay, now, how does that help us any? Well, remember, even though we don't know the functional equivalent of x, we don't know what x of t is, we certainly don't know what x dot is, we know that at a very specific point in time, we know what x is and we know what x dot is. So what that tells us is that at the point of interest, t equals 2 seconds, Vy is going to be 0.5 times x, which is 8 at 2 seconds, and x dot is also 8 at 2 seconds. 8 times 8 is 64, times a half is 32. Okay, so again, we don't know the functional form of it, but we know at this specific point in time, we know exactly what it is. Okay, now let's go get the next derivative, okay, because we're going to need the acceleration in here also. So that becomes the derivative of y dot. Now y dot is 0.5x x dot. So let's keep our 0.5 out front. The derivative of x just becomes an x dot, but we got to multiply it times the existing x dot. Okay, using the product rule here, plus x times the derivative of x dot, which is x double dot. Okay, now we're going to use the same trick. Again, we don't know the functional form, but we know at a specific time, which is what we're interested in, what these values are. So ay is going to become a half onto x dot squared, but x dot is 8, so that becomes a 64, plus x, which is an 8, times x double dot, which is a 4, so that's a 32. Okay, so I got 64 and 32, that's a 96 divided by 2, so that turns out to be 48. Okay, just like that. All right, so I'll leave it to you to go ahead and finish it out there. Just take plug those in and take your square roots and you'll be good to go. Okay, so the takeaway point here is that when we've got a parametric situation, all right, we're always going to have multiple ways of dealing with it. If we explicitly know how x or y depends on t, great. That's the easiest of all. But if we don't, we can use this chain rule trick here that I'm showing you to relate the derivatives in x to the derivatives in y, or vice versa if we should need to do that. Okay, so you got different tools there at your disposal. All right.